Last class we talked about an effect called interference. It's a property of waves, and we demonstrated that light exhibited interference. This class we're going to talk about a property effect called diffraction. It's also a characteristic or a property of waves, and that will show also that light exhibits diffraction. So that's the basic plan. Here's the specific content. I'll say something about what diffraction is and illustrate diffraction. Then we're going to talk about what's called single-slit diffraction. I'll say what that is. We'll learn how to describe it, and we'll look at some examples and illustrations, demonstrations of it. And then we're going to talk about multi-slit diffraction. Again, I'll say what that is. We'll talk about how to describe it, and we'll look at some examples, illustrations, and demonstrations of multi-slit diffraction. So to begin with, just an introduction to diffraction, and then we'll really focus on these two specific cases of single-slit diffraction and multi-slit diffraction. So what is diffraction? Diffraction is the bending of waves, or deflection of waves, around an obstacle. So an example of diffraction, of bending of waves around an obstacle, is a familiar one is sound. Sound will bend around obstacles. You can hear around corners. Water waves will bend around obstacles. They can flow around corners. And that's what diffraction is. That's the phenomenon of diffraction. Here's an illustration of the difference between particles and waves when it comes to diffraction. So on the left here, imagine I've got a wall, and I've cut two holes in the wall, two slits in the wall here. And also on the right here, I've got an identical wall, and I've cut two holes or two slits in this wall. The wall on the left, we're going to all get together, and we're just going to throw tennis balls at that wall. So we're throwing particles at that wall. On the right, we're going to get together, and we're going to wash water waves onto that wall. And so we're looking at the effect of particles striking a wall, waves striking a wall where there's a slit, or in this case, two slits in the wall. And we're going to look at the differences. So for the particles, well, lots of particles don't go through the wall. Some do, but when they go through the wall, they will just travel straight from left to right. So we just get these two pencil-like streams of particles traveling from left to right on the far side of the wall. For waves, again, a lot of waves don't go through the wall. They hit the barrier, but some waves do go through the wall. But when they emerge in all directions. They emerge as these sort of hemispherical wavelets emerging from this upper slit and this lower slit. This is the bending of waves, diffraction, and that's absent for particles. There was no diffraction, no bending of the particles when they passed through the wall. And so this diffraction, this bending of waves, whether it's water waves or whether it's sound waves or whether it's light waves, is a wave phenomena. It's not exhibited, it's not a feature of particles. And so our projects today with the single slit diffraction and the multi-slit diffraction are to look at the details of this diffraction, this bending of waves. So here's I got a couple of pictures here. We've gone to the beach. Here's some examples of diffraction of water waves. So if you look here, there are some barriers for the ocean waves. And actually you can see to the left and above the barriers, these are the ocean waves approaching these barriers. So here's a crest here, here's another one here, and so on and so forth. They look like what we would call plane waves or parallel waves striking this barrier. And this barrier is a barrier with slits in it. And so where there's a barrier, the waves can't get through, but where there's a slit, the waves can get through. Look at the waves emerging from this slit here. And it's also true for this slit downstairs here on the left, this slit upstairs here on the right. What's emerging outward is what we call these hemispherical wavelets. This is the bending of water waves around these barriers. And this is a wave phenomena. It's not a particle phenomena. So this is a very nice picture of these little wavelets, hemispherical or semicircular waves that are emerging through this barrier. You see this pattern of them here. And you see that they're actually emerging through this barrier on the left here, this region on the left here, and this region on the right here. And again, you see semicircular or hemispherical waves emerging through this left-hand hole in the barriers and emerging through this right-hand hole in the barriers. So that's diffraction. Here's another example of diffraction. Again, it's with water waves. Again, there's barriers and there's gaps between the barriers. There's slits between the barriers. Here's water waves upstairs here on the right that are striking the barrier. That blocks most of the water waves. But where the water waves get through a gap here, or where the water waves get through the gap up here, you see they emerge as little hemispherical or semicircular wavelets as they emerge out of that, out of those gaps. And again, that's the diffraction of the water waves, a wave phenomenon. So these two pictures are not the diffraction of water waves that we see in everyday life, not the diffraction of sound waves that are present in everyday life, but this is actually diffraction of light waves around objects. So this is the diffraction, bending of light waves. And these are really amazing patterns. If you look at this one on the left, which is from a single sort of long, thin slit, like a letterbox, you get this pattern if you shine red light on it. And this diffraction pattern over here is actually if you shine light on an opaque disk, an opaque circle, you get bending of light waves around the edges of the disk. And these are very famous diffraction patterns. There's a mathematical description of this pattern here. There's a mathematical description of this pattern here. But what you're seeing, where you see bright bands, either on the left-hand side or on the right-hand side, you're seeing regions where there's constructive interference of the light that passed through the obstacle or passed around the obstacle. So you're seeing these regions of constructive interference. That's why you get these bright bands. And in between them, you're seeing these dark bands. That's where you're seeing regions of destructive interference of the light that either went through the hole in the obstacle or went around the obstacle. And there really are, I put two names on here. These are very famous names in physics, Fresnel and Fraunhofer, especially in optics. They have very interesting lives. And they came up with the expressions, the mathematical expressions that describe these types of diffractions, these diffraction patterns. And they also developed a lot of the optics that allowed you to see these types of diffraction patterns. So they're the sort of, I don't know, the grandfathers or the rock stars of diffraction patterns with light. Okay. So our class is going to be a little bit about trying to quantify and explain these diffraction patterns for a single slit diffraction pattern and a multi-slit diffraction pattern. And we'll base our discussion really on that understanding of interference of waves and constructive, destructive interference of waves. So I just wanted to remind you that in this sketch here, we're seeing two waves interfere on the left-hand side. They collide with one another on the left-hand side. They superimpose with one another on the left-hand side. And because they're in phase, there's 0-degree phase difference between them, they constructively interfere and make a larger wave. And then the partner to that is, again, here we've got two waves, upstairs, downstairs. These two waves are colliding with one another. They're superimposing with one another. They're coalescing with one another. But these two waves are 180 degrees out of phase, half a cycle out of phase. So these two waves interfere destructively with one another, and they're actually canceling each other out. And those whole diffraction patterns, the letterbox diffraction pattern, the disk diffraction pattern, they're all based on this understanding of bright bands being constructive, dark bands being destructive interference. Okay. So I'm going to explain how you get single-slit diffraction. That's what this slide is. Somehow I missed out. Did I jump a slide? No, I didn't. Okay. So now I'm starting single-slit diffraction. And we're going to spend, maybe 30 minutes, 20 minutes on single-slit diffraction. And then we're going to turn to multi-slit diffraction and spend a similar amount of time on that. And as I say, we're going to look at some equations for single-slit, multi-slit, and we're going to look at some illustrations, examples. But this is to explain how single-slit diffraction occurs. This is to explain kind of the equation, the formula that lies beneath single-slit diffraction. So let's start with this picture over here. This is a sketch of some waves. They might be water waves, they might be sound waves, they might be light waves, striking a barrier that upstairs here you see a portion of the barrier, downstairs you see a portion of the barrier. It has a single slit in the barrier. And the width of the single slit is denoted as A. So A is a parameter. A is the parameter that describes the aperture in this slit. So these waves that strike the aperture will emerge to the right, and we're going to understand the diffraction pattern over here on the right by understanding how these waves interfere. And so that's what I'm going to, this is a long list of things I'm going to explain, but this is the explanation of the diffraction pattern that we'll see over here on the far right. So the first thing we're going to do in understanding the diffraction pattern, you see that gap in the obstacle, that slit in the obstacle. We're going to imagine in that gap a series of points. I've marked some of them in black here. There will be many of them, but I've just marked a few. And the understanding of the diffraction pattern is based on every one of those points as being a source or an origin of lots of little wavelets, lots of little semicircular or hemispherical wavelets of water waves or sound waves or light waves emerging from that slit. So each of these points is a source of wavelets heading out, moving away towards the right. Now, as we start thinking about these wavelets and how they're going to interfere, I'm going to divide the slit up into two halves. So I'm just going to divide it because that's going to help us. I'm going to divide it into a top half and a bottom half. And so you can see I've done that here. Like this lower half the width of the slit. This is our lower half, obviously. And this region here, this is our upper half the width of the slit. So Now we're going to compare waves emerging from the bottom half and the top half of the slit. And we're going to make an observation about the waves that emerge from the bottom half and the top half of the slit. So firstly, I'm going to compare wave number 1, so that's this one here, at the bottom of the bottom half of the slit, and wave number 3, which is at the bottom of the top half of the slit. If the extra distance that's traveled by wave number 1 compared to wave number 2, if that extra distance is a half integral number of wavelengths, so half a cycle, half a wavelength, you're going to get destructive interference. So if this extra distance here, this is just a little bit of trigonometry of a right-angled triangle with a hypotenuse that's half the width of the slit. If this extra distance here, A divided by 2 times sine theta, it's the opposite side of a triangle with theta in this corner here. If this extra distance is half a wavelength, or 3/2 a wavelength, or 5/2 a wavelength, you're going to get destructive interference. If wave number 2 and its partner, so its partner, wave number 2, look, it's at the center of the bottom half of the slit. Its partner is wave number 4. It's at the center of the top half of the slit. If the extra distance that wave number 2 travels is also half integral, i.e. half a wavelength, 3/2 a wavelength, 5/2 a wavelength, wave number 2 and 4 will interfere destructively. And you'll get destructive interference. Now, the way I've drawn this picture is not only that wave number 1 and wave number 3 are going to interfere destructively if this extra distance is half integral wavelength, and wave 2 and wave 4 will interfere destructively if the extra distance of wave 2 is a half integral wavelength, but actually any wavelet from the bottom and its partner from the top, if the extra distance is half a wavelength or 3/2 a wavelength or 5/2 a wavelength, you're going to get destructive interference. And that is how we understand dark fringes in the diffraction pattern from a single slit. So if that path difference between the waves from the bottom half of the slit and the top half of the slit, that path difference we've said is half a sine theta. If it's a half integral number of wavelengths, so 1/2 or 3/2 or 5/2, you're going to get destructive interference, and that you're going to get a bright fringe. That means that if I multiply this equation by 2, just to simplify it, if sine theta, if the direction that you're viewing the light from the slit is equal to the wavelength divided by the slit width, you're going to get destructive interference. You're going to get what we call a bright fringe. And so this is how we understand the fringe pattern from a single slit. It's governed by this little equation here, sine theta equals lambda over A, that tells you where the dark fringes are, that tells you the direction of the destructive interference. Okay. So just to summarize that, because that was a lot of explaining, even I got tired of it, we've derived this master equation. So we did a lot of work, but it led us to this master equation here for the diffraction pattern from a single slit. I rearranged it a little bit. I moved the A from the denominator on the left to the numerator over here. No, I didn't rearrange it. I actually left it the same. I just multiplied that by 2. If this equation holds, where m lambda is an integral number of wavelengths, then this is the rule for destructive interference. This is where you get dark fringes. And so this was the conclusion of the last slide. In this equation, just the stress, right? Theta is the direction of the destructive interference. A is the slit width. lambda is the wavelength of the light that you're shining on the slit. And m's just an integer, plus or minus 1, plus or minus 2, plus or minus 3, that tells you what we call the order of the diffraction minimum, or the order of the fringe, the dark fringe. So this is our master equation. If we want to look at it, here's a picture of it. So on this picture is again the slit, the aperture in the barrier. Slit width is A. Over here is a screen. The distance to the screen I've marked as L. This is the direction to some location on the screen. So this is the theta in our equation. Here's the center of the screen. We see a bright maximum there opposite the aperture. But as you walk upwards away from the center of the screen, or downwards away from the center of the screen, you'll see dark minima. So this brown line here is the intensity of the light striking the screen. You see it's bright in the center. You see other regions are bright. But we've developed an equation to describe these locations where you get a dark fringe. This location here. This location downstairs here. This location right upstairs here. And this location right downstairs here. These are described by our equations. This fringe here, dark fringe, this dark fringe here, that's when sine theta equals lambda over A. That's where m equals 1. Or where sine theta equals minus lambda over A, where m equals minus 1. Upstairs, further upstairs and downstairs, that's where m equals 2 or minus 2. So this is sine theta equals 2 lambda over A, and this is sine theta equals minus 2 lambda over A. There's another way you can write this equation. Instead of the direction to the screen, sometimes we write it in terms of the location of the fringes, the position of the fringes on the screen. And so this is the second version of this equation. Obviously, they're related, closely related to one another by just a little bit of trigonometry. So the last equation was the direction, theta, of the dark fringes. This equation is the position y on the screen of the dark fringes. You can get this equation from the prior equation just by a little bit of trigonometry and what we call the small angle approximation. The small angle approximation applies when these distances on the screen are much smaller than the distance from the screen to the slit, which is normally the case. Anyway, here's this equation. So it's a second version of the prior equation. And instead of theta, we've got y. This is the position on the screen rather than the sign of the angle of the direction towards the screen. But again, we see the slit width, we see the distance to the screen, we see the wavelength of the light, and we see an integer m that is the order of the dark fringes. So there's dark fringes where the first order dark fringes when m equals plus or minus 1, the second order dark fringes when m is plus or minus 2, third order dark fringes when m equals plus or minus 3. Okay. Let me, after all that, I think we need the break. So, I mean, not a nap, a demonstration. I want to show you, I'm going to show you a video and I'm going to show you a demonstration. They're both really kind of short. So I've got this is an experiment we saw last class. It was the double slit experiment, but we can set it up with a single slit as well. I can shine light on a single slit, and we can see the diffraction pattern. And so I've got a laser in here, extremely powerful, dangerous, and I've got a single slit over here, and I'm going to switch on the laser carefully, shine the light on the single slit, and it's going to shine on the screen here. We're going to see the diffraction pattern. So we believe in this diffraction pattern. Look, we believe that waterways diffract when they go through a gap in aperture in a barrier. We believe that sound waves do because we hear around corners. But let's believe that light also exhibits diffraction. And so on the screen here, I don't know if right at the back of the room you'll see, but on the screen here, there's a whole sequence of tiny dots. Tiny green dots, which are the constructive interference of the light, and between them are tiny dark regions, which is the destructive interference of the light, which is what we've learned how to describe. So this is literally a diffraction pattern from a single slit, literally what we've been describing mathematically, with a slit that's some fraction of a millimeter wide and some green laser light. I'll show you a video of this in which in the video, I'm actually going to change the slit width. I'm going to vary the slit width, and you're going to see when I vary the slit width, the pattern changes. Actually, if I make the slit width smaller, the pattern will stretch out according to our formulas. And if I make the slit width wider, the pattern will compress. So we'll see that. And so I'm adjusting the slit width, and look at that pattern stretch out as I adjust the slit width. I'm actually making it narrow. And I completely shut it down. And now I'm making it as, may have said that the wrong way around. Okay. I don't know why I clicked on that. I missed the... So in that video, take a look at this equation here, because I got a feeling I said it wrong in my excitement of making that video. What happens if I make the slit width narrower? So I make A smaller. Then the pattern's going to have to expand because over here on the right-hand side of the equation, this is just whole numbers of wavelengths. So if I make A smaller, I've got to correspondingly make Y bigger. So making the slit narrower expands, stretching the diffraction pattern. And making this slit wider compresses, shrinks the diffraction pattern because over here is sitting simply multiples, integers of the wavelength of light. Here's just a picture of this second version of the equation in which we're recording the positions on the screen of the dark minima. So here again is the slit. The light is passing through the slit. It's diffracted by the slit. We're getting constructive, destructive interference. This in brown is the intensity of the light. There's a bright spot in the middle. There's a couple of bright spots upstairs. There's a couple of bright spots downstairs. We're learning to describe the location of the dark minima. The two closest dark minima are the first order dark minima. This is their locations. They're at plus or minus lambda L divided by A from the central spot. So that's their locations. And then they're followed further upstairs, further downstairs. They're followed by the second order dark minima. That's when M is plus 2 or minus 2. And here's their locations. Their locations on the screen. And of course, if I had a bigger screen, we'd see way up here the third order, way down here, third order, then beyond that, the fourth, downstairs here, beyond the third, the fourth, and so on and so forth. Okay, let's look at an example calculation involving diffraction. So in this particular case, we're going to shine microwaves. So we open the microwave door, And we're going to shine microwaves on a window. And we're going to look at the microwave diffraction pattern on a wall downstream of the window. So we're told in this particular problem that the microwaves that we're shining on the window are 5 centimeters wavelength. We're told that the window has a width of 36 centimeters. And we're told that the distance to the far wall, the screen, is 6.5 meters. So look, this is a kind of disguised single-slit diffraction setup. We've got a source of waves. They're microwaves, and the wavelength was 5 centimeters. We're shining them on a single slit. That's the window. The width of the single slit is 36 centimeters. It's the same sort of scale as the wavelength of the microwaves. It's longer, but it's not much, ridiculously long wide compared to the microwave wavelength. So we're going to get a diffraction pattern. And then we've got a screen downstairs, which happens to be a wall, but it's 6.5 meters away. So it's exactly the setup, single slit setup that I've been describing. Okay, so we want to calculate, the question asks us to calculate whether we want it or not, the distance between the central maximum, so there's a bright spot here of microwaves, and the first order minimum. There's a dark fringe upstairs here. There's a dark fringe downstairs here. If it's the first dark fringe, then it's m equals plus or minus 1, that fringe. Okay, so let's do that. So I'm actually going to do it two ways. I'm going to do it, firstly, with the equation that describes the position of the dark fringes on the screen. And so I'll calculate the position of this first order dark fringe in that way. But then I'm going to say to myself that that's only approximation. So then I'm going to check using the exact equation, which tells me the direction to the screen of the dark fringe. And from that direction, I'll calculate the position, and I'll compare the two. So this is me comparing the two ways that we describe the locations of the dark fringes, either with directions or with positions on screens. And this is me thinking about one of them being exact and one of them being approximate. Okay, so I'm going to write down here my starting point. Okay, so this is the equation that describes the position of the dark fringes, so that's y, on the screen. When you shine a certain wavelength on the aperture has a certain width, A, and the screen has a certain distance from the aperture, L. I've just filled in that I'm thinking about the first order dark fringe. And so I filled in m equals 1. So originally we had written this equation with an m in there, multiplying the lambda. I want to find the location on the screen. So I'm going to actually be careful here. I'm going to put y1 on here because it is the first order dark fringe. And I'm going to rearrange this equation for y1. It's not hard, but if you stand up here, it's impossible. So I've rearranged it by dividing through by A and multiplying through by L. I can now stick in all the numbers, of course. Our wavelength, if you remember, was 5 centimeters. So it's 0.05 meters. Our distance to the screen was 6.5 meters. And our the width of our slit, which was the window, was 36 centimeters, so that's 0.36 meters. So I filled in all the numbers, and if I do this calculation, of course I've already done it ahead of time because I'm an extremely well-prepared person, is 0.9 meters, 0.90 meters. Let me put the 0 in here. And so that's where I'm saying there's going to be a dark fringe on the wall behind the window. So there's going to be a bright microwave spot in the middle, and then if you walk 0.9 of a meter to the left or right of the center, you're going to see a dark fringe of microwaves where there's destructive interference. So this calculation was approximate. This formula was approximate. The exact formula is that a sine theta equals m lambda. Now, again, I'm thinking about m equals 1, so I'll just write it for m equals 1. And I'll also be careful that this is, I'm going to hang a 1 as a subscript on the theta because this is the direction of the first dark fringe. So let's redo this calculation, but this time let's calculate theta. And then once we got theta, we can use a little bit of trigonometry in the right angle triangle up here to calculate y, and we're going to compare them. Okay, so theta 1, if I want to calculate theta 1, I would divide through by a, and I would take the inverse side, the arc side. So again, I can't think straight up here, but dividing lambda by a and taking the inverse sine will give me the angle theta 1. And again, if I put in the numbers, let's do that. I've got 0.05 meters. That's the wavelength. I've got 0.36 meters. That's the aperture width. And I've already calculated this, of course, because I'm extremely well organized. This was 7.93 degrees. So that's the angle. So at this point, look at this right angle triangle upstairs here. We know the angle in the triangle. We know the adjacent side to the triangle. We want to know the opposite side of the triangle. What's that trigonometric function that relates the opposite and the adjacent? I'm remembering it's tan, that tan theta equals opposite over adjacent. Or I can write it as the opposite equals the adjacent times tan theta. So y1 is the opposite. It's opposite the angle. L is the adjacent, is next to the angle. And here's my trig function, tan theta. Tan of the angle, the direction that we just calculated. So again, if I plug in all the numbers here, I've got 6.5 meters times tan of 7.93 degrees. And this came out to be 0.91 meters. Okay. So what we just learned was, well, look, we could go about this calculation of the location of the dark fringes in two different ways. We could go about it in an exact way, where we're calculating the directions, or we could go about it in an approximate way, where we're calculating the positions. If the distance to the screen is much bigger than the locations of the fringes on the screen, your approximate method will be a good approximation. You get the same result as the exact method. And that's what we're basically finding here, right? The distances of the dark fringes on the screen, well, their locations on the screen were 0.9 meter, and that's relatively small compared to the distance to the wall. That was 6.5 meters. And that's why we got pretty close with the approximate calculation rather than the exact calculation. Okay. quiz question, which means I've got to find the quiz. So in this quiz question, we're told that we got a single slit diffraction pattern. We've got light, water waves, sound waves shining on a single slit, and we're going to increase the width of the slit. So we're going to increase this slit width. What happens to the separation between the dark fringes? What happens to the diffraction pattern? Do they get closer? Do they get further apart? Do they stay at the same location? I'll give you a minute or two to think about that. Okay, so if you make the slit narrower in a single slit diffraction pattern, you make the pattern stretch out. You make the distance between dark fringes grow. And so making the slit width smaller grows the distances between the dark fringes. It's really because you've got to arrange that the wavelets that are coming out of the slit interfere destructively. If you compress them into a smaller slit region, smaller aperture, you're going to need more space on the screen, more angle towards the screen for them to interfere destructively. So that's one way of sort of thinking about it. But in the equation, the other way to see it in the equation is, for example, we wrote down the equation A times Y divided by L is an integer number of wavelengths. If you make A bigger, you've got to make Y smaller. If you make A smaller, you're going to make Y bigger to get that integer number of wavelengths. So you can see it in the equation, this relationship, or you can think about it in terms of what you need to make destructive interference from the little wavelets that are emerging from the little slit and heading towards the big old screen. I'm going to skip this one, and I'm going to move on to multi-slit diffraction. And here's just a picture. We call this a grating. It's something that creates a multi-slit diffraction pattern. It's a whole array of many slits. So each one of these vertical light-colored lines is a slit. And so if you shine light or you shine other waves on this, you've got now many, many slits, many, many apertures that the light will pass through. And when the light passes through those different apertures, again, the light or the water waves or the sound waves, because they're waves and they exhibit diffraction, they'll bend around the slits, they'll be deflected by the slits, and all those waves passing through all those slits will interfere with one another. And you get actually what is really a beautiful sort of classic diffraction pattern from this multi-slit arrangement. We call it a diffraction grating arrangement. Now, just one point. In the single slit case, we developed an equation describing the single slit diffraction pattern. The parameter was the slit width. So A was the parameter of the obstacle that created the diffraction pattern. In this case, for the multi-slit diffraction pattern, the parameters, not the slit width, it's the slit separation. So you're going to see a D rather than A, and that D means the slit separation, not the slit width. So what's important here is the space between two adjacent slits. That will determine our diffraction pattern. So that's one difference. The other difference that's going to come up, the equation that we used to describe the single slit, it was an equation. We developed that equation for the location of dark fringes, constructive interference. In the case of the multi-slit, we'll develop an equation, or we'll write down an equation that describes the location of bright spots or bright fringes. So that's the regions of constructive interference. So the equations are going to look the same, but there's two fundamental differences between single slit, multi-slit. In the one's describing a single slit with a width, the other one's describing multiple slits with a separation, and then the other difference is that one's an equation for destructive, the other's an equation for constructive interference. Okay. This is just to show you, if you wanted to take a stroll from single slit to multi-slit, well, the stroll would be, well, first you do 2 slits, then you do 3 slits, 4 slits, 5 slits, and so on and so forth. And you could watch on your stroll from one slit to multi-slits how the diffraction pattern changes. It would be a wonderful thing to do if we had time. Well, here's at least pictorially what happens. So here's a single slit diffraction pattern. This is the bright fringe in the middle, and I don't know if I can just about see it. There's a dark band here, and there's another bright maxima over here on the left, and similarly over here on the right. There's a dark band. We learned how to describe that. And then there's a very faint but bright maximum over here. You go to 2 slits, you get this sort of pattern here. This pattern of bright and dark, bright and dark, bright and dark. Constructive, destructive, constructive, destructive interference. Go to 3 slits, you get a similar sort of pattern, but you see an interesting thing starts to happen as you go to 3 slits, and as you go to 4 slits, and as you go to 5 slits, and as you go to more slits. The location, what happens is, the locations of the bright spots become smaller and smaller and smaller, so you just get occasional bright spots. The locations of the dark regions become larger and larger and larger. And so when you go to, we got 1, 2, 3, 4, 5 slits here. Multi-slit, by multi-slit, I might mean 1,000 slits or 10,000 slits, so a huge number of slits. What you get then is these locations, it's a fantastic pattern. You get these locations of intense bright spots with these great deserts between them of destructive interference. Let me show you that. I was going to remind you about constructive and destructive interference, but I think we know that now. This is multi-slit diffraction pattern on this overhead here. This is from thousands of slits, the diffraction pattern. This is from what we call a diffraction grating, its diffraction pattern. Here we're seeing the diffraction patterns with 3 different colors of light. So upstairs is a sort of blue, rather nice, I think, blue-violet light. We got a very calming green light in the middle here, and then we got a red light downstairs here. Now, we know, right? We know the meaning of color since we come in this room. we know that color is related to the wavelength. Blue light is short wavelength, green light is intermediate wavelength, and red light is long wavelength. So up here, we've got something like 400 nanometers. Downstairs, we've got something like 700 nanometers. Green light is somewhere in between those. So we're changing the wavelengths. We're shining these different colors, wavelengths of light on the same diffraction grating. So you see that on the diffraction grating, you stretch out or compress the diffraction pattern, the interference pattern, as you change the wavelength. So you could imagine, this is a clever idea, I just had it. You could imagine using one of these to measure wavelengths of light. And that's often what diffraction and gratings are used to very, very precisely measure wavelengths of light. Anyway, what you're seeing, let's take the blue diffraction pattern. Here's a bright fringe in the middle. What about these two bright fringes or spots on the left and right? Those occur where the path from every single slit, so you might have 1,000, 10,000 slits, is different by whole numbers of wavelengths. So that's a very, very special occurrence, because in general, the path to the screen from all the individual slits would be all sorts of odd numbers of fractions of wavelengths. But there's certain locations, special locations on the screen, where the path to that location on the screen from every slit is a whole number of wavelengths. You get a bright spot at that location. You get bright constructive interference at that location. And that's true for these other spots too. At those other spots too, those are the special locations where from every single slit of those 1,000 or 10,000 slits, the difference in paths for all the slits is a whole number of wavelengths. And so you get constructive interference. Everywhere in between this destructive interference desert that I described, in between the bright spots, then that condition doesn't hold. You got all sorts of path lengths from all sorts of fractions of a wavelength difference from the different slits. And so you just get some overall destructive interference. And so that's how we get this, this pattern here. Let me show you a video. So I'm going to show you the video, and then I'm going to give you a chance to look at this yourself, because we've got a demonstration here. But what we have here is a special type of lamp. This one has, this lamp here has neon in it, and neon produces a certain color of light, a characteristic color of light. And we've got other ones that, look, this is helium, and this is hydrogen, I think it was. They produce their own colors of light. Now, you just look at the lamp. I know it's mesmerizing, but it just looks like some sort of orangey red color of light. But if you look at it in a diffraction grating, you see an amazing thing. That reddy orange color of light is split up into all these separate spots of light, because it's really a blend, a superposition of certain frequencies, certain wavelengths, certain colors of light that is characteristic, that is a signature of neon. And so in a diffraction grating, you can see neon's signature, see neon's fingerprint. And so I'm going to show you that in these little videos here. So this one is hydrogen. What you're going to see right now is hydrogen, and I'm looking at the hydrogen lamp in a diffraction grating. I didn't show you the diffraction grating. This is actually the diffraction grating. I'm going to pass these around shortly. On one of these, just looks like a piece of clear plastic. But it's not just a piece of clear plastic. It's actually got thousands of lines etched on it. And so you can see diffraction grating, diffraction patterns multi-slit diffraction patterns by looking into these little slides here, because they literally are diffraction gratings. So this is a movie of using one of those diffraction gratings with the hydrogen lamp. And this is the pattern that we saw. These different, look, there's violet at one end, there's red at the other end. This is the signature of hydrogen. Bit of a short movie, so we'll show it again. I can't even get enough time to slow it down. I'm showing it multiple times because it took us like an hour to make it, and it's 2 seconds long. But that pattern of light is hydrogen's signature. And when you see that pattern of light, you're seeing how hydrogen works, really. You're seeing the true nature of hydrogen in the colors of light that it emits. I got another one. I think this one was helium. Again, there's different colors of light in there. You can see red, blues, and violets, and that's helium's signature. So what I'm going to do, I'll put this lamp back on, and I'm going to pass these things around. And you can see if you can look into these screens and see the diffraction pattern. So I'll send a couple back over here. Each one is worth thousands of dollars, so I want to get them all back. Oh, but I need one. Hold on. I've got to show you how to do it. Can I go? Okay, so the first thing is that you're all doing it wrong, right? The natural thing is to point it towards the light and look at the light. You're not going to do that. You're not going to look through it at the light. Let me show you. Let me show you an example. I'm going to stand here, and I'm going to have. Right now, I can see the diffraction pattern. It's really amazing. The yellows and the reds, and I can see some greens and so forth. But look, I'm not pointing the diffraction grating at the light. I'm looking off towards the side. And so if you're near the front, do something like this. If you're at the back over here, or if you're at the back over there, look towards the door here. If you're on this side, point it towards the door there on that side, and you might be able to find it. And you just got to walk around a bit. If you're over... Do you have one? Yes. Okay, who saw it? Nobody. Oh, that's good. Quite a few people saw it. It is amazing. Once you get it, I mean, you're looking around, you're thinking this is ridiculous, and then you suddenly find it sitting out there. And it's this amazing sight, if you didn't see it, these vertical bands of different colors of reds and oranges and greens and blues. And that's a diffraction grating. And you're literally seeing the signature of this lamp, the neon lamp, what neon is all about. And you're literally seeing these bands of constructive interference from the thousands of slits on one of these gratings. So it's really quite an achievement to see all that. Okay, so I want to show you ultimately the equation that describes the bright spots that you may or may not have seen. So here's a sketch. Here is light, sound, water waves striking a diffraction grating. So over here on the left-hand side, we got many slits in our diffraction grating. Of course, I've said there's thousands or 10,000s of them rather than these 5 here. Here is a screen we're going to direct the diffraction pattern onto. And we've said again, and we may have seen, you get a bright spot in the center. But what you were looking at was most likely the first order diffraction maximum upstairs here, or the first order diffraction maximum downstairs here. And those diffraction maxima, so the one upstairs here and the one downstairs here, are some angle theta. It's indicated here. So here's an angle theta, here's an angle theta, away from the bright spot, away from looking directly at the light. So if you look through the diffraction grating directly at the light, you're seeing this thing here. You don't see it split into all these patterns of different colors. If you look away from the lamp, over there or over here, you see this first maximum and this first maximum down here. This is where the paths from all the slits differ by whole numbers of wavelengths. And this is where you're seeing the diffraction rather than the direct light. This is not a great, I don't really like this picture because the reality of it is that this is so far from scale, it's ridiculous. This should be stretched out towards the left through this far end of the chemistry building. This should be stretched out towards the right through the physics end of the chemistry building. So the scale is completely wrong on this picture. But it does carry the message that there's a bright spot in the middle where light just streams straight through. And then to the far upstairs here, far downstairs here, you see these bright diffraction maxima where we're getting constructive interference from every single slit of the 10,000 or 1,000 slits. Okay. This is the extra distance that's traveled by light from one slit compared to an adjacent slit. So this is a little bit of trigonometry, and this is this extra distance from one slit to the next slit when you look at an angle with respect to the slit. And if that's a whole number of wavelengths, as I described, so m lambda, where m's an integer, then this is the condition, this is the equation for constructive interference. This is the location of the bright fringes. It looks exactly like the equation for the single slit, right? Except in this equation for the multi-slit rather than the single slit, we've got a parameter D rather than a parameter A. D is the slit separation. A was the parameter of the slit width. So that's a difference. Also, again, this is an equation for the bright spots, the constructive interference. With the single slit, it was an equation for the dark regions, the dark fringes, destructive interference. But anyway, it's the same looking equation. And so let's take a moment and let's work through an example. Let's work through an illustration. So here's an example or an illustration. We're told, in this case, this is an example involving visible light. And we're going to shine visible light on a diffraction grating or a multi-slit arrangement. And we're told that the diffraction grating has two 2,000 lines per centimeter. And we're told that we're shining red light, wavelength 640 nanometers, on the diffraction grating. And we're going to find the angle of the first maximum. There's one point here. People use diffraction gratings. They're supposing I use diffraction gratings, which I don't. But supposing I did, if I was telling my friend who also used diffraction gratings, about my diffraction grating, I wouldn't say the slit width. They always say the number of lines per centimeter. So that's kind of the language that is used for diffraction grating. So that's why this question says you've got a diffraction grating that is 2,000 lines per centimeter. Now, what that really means is, in terms of slit separations, is that, well, if 2,000 slits are spread over a centimeter, then 1/2000th of a centimeter is the distance between adjacent slits. So you can always calculate, knowing the number of lines per centimeter, the slit separation by dividing the centimeter by that number of lines per centimeter. So that's just a bit of technical language that they use for diffraction gratings. Anyway, we've got to take this information and we've got to find out the locations of the first order maxima of the red light. So let's see if we can do that. Okay, so here we are, and of course, like any physics problem, I'll make a nice diagram of the physics problem. Over here on the left is the diffraction grating, standing vertically. Over here on the right is the screen, standing vertically. The diffraction grating, we were told, was 2,000 lines, 2,000 slits per centimeter. So actually, to figure the slit separation between adjacent slits, I've taken a centimeter and I've divided it by 2,000. And so that would be actually the distance between adjacent slits in centimeters. I also then divided it by 100 to convert it into meters. And I got this number here. 5 times 10 to the minus 6 meters is the distance between adjacent slits. So we know this number D. We know the wavelength of the light that we're shining on the multi-slit diffraction grating. We're shining light that's red, 640 nanometers. It's long wavelength visible light. We've got to figure out the angle to the first diffraction maximum, so that there's a first diffraction maximum upstairs here. This is the first bright spot away from the central bright region. There'll be another one downstairs here at the same angle. It would be, say, y minus 1. This is where the integer m would be plus 1. The order m would be plus 1. The integer m would be minus 1. Okay. So we want to find this angle. So that master equation for, that's wrong. That master equation for the multi-slit diffraction pattern is d sine theta equals m lambda, where m is that integer, plus or minus 1, plus or minus 2, so on, so forth. It's the order of the diffraction pattern. In our case, we want the m equals 1 diffraction pattern. And so our equation here is just going to be d sine theta equals lambda. And I'll hang a little 1 subscript on my theta because I'm referring to the first order maximum. We want to rearrange this to find theta. So I'm going to divide by d, obviously. I'm going to take the inverse sign. And so we're going to get inverse sine of lambda over d. And now I can just fill in the numbers. Inverse sine of, it's 640 nanometers, so that's actually 6.4 times 10 to the minus 7 meters. Oh. And I'm going to divide that by 5 times 10 to the minus 6 meters. Come on, pen. So I get this little equation here. And if I plug in the numbers, of course I'm super well organized, I've already done this, 7.35 degrees. That's the location of the first bright maxima away from the central spot. There would be other ones that are further away. We could find them if we plugged in m equals 2, m equals 3, and so on and so forth. They get increasingly hard to find, to locate, because they get increasingly duller, less bright. But there's a whole pattern of them. Anyway, that's an example of a diffraction grating. And there's one more example I had, but I think I'll just post it. Let me end up with a summary. Yeah. What was today all about? Sometimes I get home after a hard day at work and I think, what was the day all about? And sometimes I wonder, what was the class all about? Class was about diffraction. Diffraction is the bending of waves around obstacles or when they pass through obstacles. Diffraction happens for water waves, sound waves, light waves, other types of waves. We looked at two very special cases of diffraction. Single slit diffraction, where we could describe the dark fringes with an equation. Multi-slit diffraction, where we could describe the bright spots with an equation.